For this video, I'll be working through question 4 of the 2017 Scholarship Physics exam. LCR circuit below is driven by an AC source at an angular frequency omega. Show for the case where the reactance of the inductor is greater than the reactance of the capacitor, that tan of the angle phi, this is the phase angle, is equal to the reactance of the inductor minus the reactance of the capacitor divided by R, where phase is where phi is the phase angle between the voltage source and the current. Right, we'll draw like a wee phasor diagram just to make life a little bit easier. Here we go. This is XC. Try and make that C. This is R. This is the resistance. And this is going to be XL, which in this case is going to be bigger. So the total impedance, Z squared, is equal to R squared plus XL minus XC. You can obviously, this is a magnitude, so it doesn't really matter if XC is it's XC minus XL, because it makes it a positive number regardless, because this here just finds a difference, but whatever. It's a strange question to ask. When XL is greater than XC, so the reactance of the inductor is greater than the reactance of the capacitor. We'll draw a little picture to show, just because that's probably the only way I can think about it. This is Z. Here we get, this is the resistance, and there should be a phasor diagram there, and this should be another vector, and this is going to be XL minus XC, which is equal to, I'll just put this over here, reactance total is equal to XL minus XC. In other words, as we can see here, this angle here, phi, tan phi is equal to the opposite, so this here up here is equal to XL minus XC divided by the adjacent, which is R, which is equal to, what is it equal to? Omega L minus 1 over omega C. Let's put brackets around that, divided by R. That's, yeah, I don't really know what it's trying to ask. It's just common, well, it's not common sense, but it's basic principles for a circuit, but whatever. Explain using physics principles what happens when what happens to the angle phi when the capacitance increases. So I'll pause the video, answer it, and then go. So I've said when capacitance increases, capacitive reactance decreases, as the reactance is the inverse of the frequency times the capacitance. So as the capacitive reactance XC decreases, the total reactance increases, because total reactance is reactance of the inductor minus the reactance of the capacitor, thus increasing the phase angle phi, which you can pretty much see up there. Right, next question. When the switch is in position 1, so we're going to look at, this is the diagram here, we have to keep on going back and forward to it, but whatever. When the switch is in position 1, the RMS current is 1.5 amps. The switch is now moved to position shown on the diagram so that the resistance is included in the circuit. The source voltage lags the current by 30 degrees. Show that the reactance is 214 ohms. So we'll just have a look at things. When the switch is in position 1, it is just an LCR circuit, and the RMS current is 1.5 amps. So we can just we'll find out the total reactance, because that might help us later. So the voltage is equal to the current times the impedance, and the impedance is just the reactance plus the resistance. In other words, here we go. At position 1, we'll just have a quick look at this actually. At position 1, it's not an LCR circuit. The electrons come down here and it shorts the resistor, so it's just an LC circuit. When it goes to position 2, it is an LCR circuit with two capacitors in parallel, and these two capacitors are identical, so they'll just add together, which will double the capacitance, which should half the reactance of the capacitor. There we go. That's a lot of a mouthful. Right. So the first time it's just an inductor and a reactor. So we can an inductor and a capacitor. So VRMS over IRMS is equal to the total reactance, because that resistor has been shorted, and that is just going to be equal to 185 divided by 1.5, which gives us 123.33 ohms. It's not too hard. And just noting that the total reactance is equal to X, C minus XL, or either way, it doesn't really matter. Right, now we have, it says that the source voltage lags the current. Okay, so yeah, that works pretty good, because the capacitor has to be bigger than the what do you call it, inductor reactance. The capacitive reactance has to be bigger than the inductive reactance because it lags by 30 degrees. And we'll just draw that now. So we'll go, here's our diagram. Here's our impedance, which is lagging, whatever that is. Our phase angle phi. Our resistance, which, do we know what the resistance is? No, we don't. Does it matter? Probably not. Because we know what phi is. Oh, we've got everything. And this is our total XT, because that's just the reactance of the inductor minus the reactance of the capacitor, because it's lagging, it's down. In other words, tan theta is equal to the opposite over the adjacent, which is equal to XT divided by R. We're trying to find the resistance, is 214. Easy peasy lemon squeezy. We have moved the resistance up, tan theta under. R is equal to total reactance, which is this here, divided by tan theta, phi I should say. Why am I calling it theta? It's phi when it's dealing with electrical circuits, which is equal to 213.619 ohms. Oh, look at that. Oh, yes, 214. That's what we're trying to show, which equals 214 ohms. The switch is now moved to position 2. The source voltage now leads current by 15 degrees. Show that the reactance of the circuit is given by the following expression. So we have two capacitors, capacitors in parallel, caps, I'm going to shorten that, and parallel give 2C, which is, it's just the opposite how you add resistors in parallel. Thus, the reactance of the capacitor is now 1 over 2 C angular frequency, or omega, as, can we see that's right, as phi, the angle, is now greater than 0. This means the reactance of the inductor is now greater than the reactance of the capacitor, so the inductor, or the phase angle, leads the current. That tells us that the inductor reactance is bigger than the capacitor reactance. So I'll just do a diagram here. Here we go. Here's the resistance. This is the total XT. Notice of, and here's phi, which is positive, and this is the impedance here, Z. There we go. So what do we have? We have tan phi is equal to the opposite over the adjacent, so XT, total reactance, over the resistance. We'll just rearrange this. In other words, R tan phi is equal to XT, which is equal to the inductance of the reactance of the inductor, so the fancy resistance of the inductor, minus 1 over 2 omega C. I should have put brackets around that, whatever, which equals 214, because we've got the resistance up there, times tan, was it 15? Yep, make sure your calculator is in degrees, and that is roughly equal to, or it is equal to, let's put down here, 57.34 ohms. In other words, it's equal to 57.2 ohms. It's just because I got rounding errors, because I rounded, I think I might have used that one there, but close enough. Right, Determine the values of the inductance L, capacitance C, and angular frequency of the source volt if of the source voltage is the angular frequency of the source voltage is 350 radians per second. Right. So we know omega L minus 1 over 2 omega C from above is equal to 57.2 ohms. We know that. So we're trying to find the values of the inductance and capacitance. And we have that there. So we're just assuming all the other stuff that we've had previously is true. We also know with just one capacitor, 1 over omega C minus omega L is equal to 123.33, and that was the first one up here. So we're using these two, and if we use a little bit of simultaneous equations, if we have two unknowns and we have two equations, which means we can solve this. It is solvable unless, yeah, it is solvable unless one of them relies on the other. But it's not like that. Right, so we're going to go one. We're going to add. What are we going to do? We shall add these two equations together. So we're going to get. What are we going to get? We're going to 1 over omega C plus omega L from this one up here, minus omega L, because I'm going to add these two equations together, minus 1 over 2 omega C. That is going to give me 123.33 plus 57.2, which means 1 over 2 omega C equals 180.53. I've already done the working on like a spare piece of paper. This is why it's so important to have like pad paper, so you can do this on your calculator. This just shows the logic. So in other words, C, because we know omega equals 3.5 times 10 to the 2, you can rearrange to find C equals 7.91 times 10 to the minus 6 farads, which is pretty reasonable. It's, yeah, 6 microfarads. I mean, about 8 microfarads. That's a decent capacitor. So, and then if you plug this here back into one of these and rearrange, you'll find that L is equal to 0.679 henries, which is big but not impossible.